morning, everyone. Welcome to the second day of the IFDS Workshop. Today, we are having a nice morning session about reinforcement learning. And our first speaker is Jiang from University of Illinois Urbana-Champaign. He got his PhD from University of Michigan and did a postdoc at MSR New York. Is that right? Yeah. And then joined the UIUC and has been a faculty member there working on theoretical foundations of reinforcement learning. And he has got a bunch of different awards like the NSF Career Award, the Sloan Award, Google Research Award, plus some Best Paper Awards. And today he will tell us about a new viewpoint in reinforcement learning.
Thanks for the introduction, and thanks everyone for coming. So I work in RL, and I'll today tell you something about RL from a view that some of you may not have heard before. Okay. So we've seen impressive success of RL, in all kinds of games, board games, video games, or even fusion reaction simulations. Now, while these successes are very impressive, if you look closer into these cases, the commonality is that they all happen in simulators, right? Where we have unlimited amount of training data. Basically, the only limitation is our computational budget, and we can basically learn by trial and error and just be free taking any action we want without ever worrying about the consequences of taking suboptimal or even risky actions. On the other hand, many important potential applications in RL do not come with high-fidelity simulators, such as in medical scenarios or online recommendation. And this is particularly true when humans are part of the environment that we're trying to optimize on. And even in some highly complex physical systems, we can't fully rely on the simulators. The simulators are not going to be perfect and may need to close the sim-to-real gap using some real-world data. And in such scenarios, the majority of our algorithms that rely on the conveniences of simulators are no longer directly applicable. So to tackle this challenge, the RL community has reached the consensus that offline RL, where we train agents solely based on pre-collected data, is an important paradigm for bringing RL to real life. Now, it's been a few years, and thousands of papers are published on the topic. But you may ask, what are the applications, right? Why are we not seeing offline RL deployed in real-life tasks everywhere in every aspect of our life? Okay, so that's the main question, or I want to provide one reason for why this is the case. As a side product, my talk will also touches on the very theoretical foundations of RL, right? So, in RL, eventually everyone wants to address high-dimensional, complex environments with high-dimensional state or observation spaces, where we need to use neural networks to generalize. But however, to build a theoretical foundation, we often need to first simplify the problem. And traditionally, the way we did it is that we move away from the complex environments, look at these toy problems with finite and small state spaces, and then, this is so-called, the tabular setting. This is like the standard picture that you get from Wikipedia page of what an MDP is. And what we do is that we develop a mature understanding there and develop the right algorithms, and then we extend the algorithm and analysis back to the complex setting. So the question is that the only way to build a theoretical foundation, or there are alternative formulations that should give us fundamental insights that have just eluded us for years? Well, as a little spoiler, one concrete approach you can think about is not to simplify the environment, but to simplify the hypothesis space, right? And exactly as how we do it in learning theory, right? So we're still going to consider the high-dimensional complex environments, and that will be the case throughout the entire talk. But what if we don't think about neural nets, but let's say start with a finite hypothesis class? Or even simpler, how about I ask you to simply compare two candidate hypotheses? And trivial as it may seem, and indeed this question is literally trivial in supervised learning, a version of this question, which I will talk about later, had been open in RL for more than 20 years. Okay, so let's start with my main question, which is why we're not seeing offline RL everywhere in real applications. And to answer the question, we can look at the most mature ML paradigm, namely supervised learning, right, and see what lesson we can learn from there. And speaking of supervised learning, I think many will directly jump to what kind of algorithms we use, optimization, neural architecture, and so on. But I would say that the massive real-world success of supervised learning depends on something that is much more fundamental that we often take for granted. That is, when you get your hands-on data set, the first thing you do is not to run your favorite training algorithm, but to split it into train validation tests, right? You can try as many things, as weird things you want on the training set, and eventually rely on the validation data set and eventually the test set to tell you which one is best performing and how good it is. Okay, so now, given the similarity between offline RL and supervised learning, that in both cases, you just have a data set, and eventually you want to output a machine learning solution, maybe we should do something similar in offline RL, right? And of course, we can do the same split of data, but the question is really like, how can we compare different training algorithms in RL? Now, recall that in RL, the final policy is, so final output is a policy, right? It tells you like, what kind of actions you should take in different situations. So therefore, the validation task is to essentially evaluate or compare the performance of these policies, right? And since these policies generally want to take actions different from those taken during data collection, we're in this so-called off-policy evaluation or OPE problem. Okay, so let me briefly, delve into this problem and see what's the typical approaches. And this will also allow us to quickly over the basics of RL and make sure everyone is on the same page. Okay, and by the way, feel free to interrupt if you have any questions. I'm happy to make this as interactive as possible. Okay, so in RL, as usual, we think about sequential decision-making, dynamical system, where upon observing state ST, you take action AT, you get reward RT, transition to the next state ST plus 1 randomly according to the transition distribution. You have a policy that maps states to distribution of reactions, and a policy's ultimate performance is determined by this expected return, which is the expected sum of discounted rewards from some initial state of interest in S0. Okay, so the goal of policy evaluation, as defined in this talk, is to estimate the scalar value for any given policy pi. Now, the goal of training, which is often policy optimization, is to find a policy that maximizes or hopefully approximately maximizes this objective. So how do we do policy evaluation, right? So that's our focus for now because we want to do validation. Like you already have policies and we want to compare them. Okay, so it turns out that a very useful way to do it is to first estimate the value function, here the Q function. The Q function tells us the expected return when you start from a particular state action pair. So once you get the Q function, the J pi, the scalar expected return value, is simply the Q function evaluated at the initial state. Right? And how do we estimate Q pi? Well, we know that Q pi satisfies the Bellman equations that essentially talks about a certain kind of temporal consistency that your prediction today should be consistent with your prediction tomorrow. In the basic theory of RL, what you're told is that if you can enforce such equation as a constraint on every single state action pair, you're guaranteed that you can recover Q pi as the unique solution. Okay, so of course, that's not going to happen in any problem of realistic interest, right? So in any practical problems, we have a enormous number of states. So what do we do instead is often to featureize your state or observations, write down a parametric form, for example, a neural net, and trying to approximate Q pi, right? And the typical way to do it, and the algorithm we're going to look mainly today is called a Federico evaluation, or FQE. What it does is that it solves a sequence of least square regression problem iteratively, where the regression target, right? So you're predicting this from here, but your prediction target, depending on this fk minus 1, is the output of this iteration from of this algorithm from the last iteration, right? So this is an iterative algorithm, and the expectation here is over typically whatever data you have. We typically treat it as a distribution of tuples, where in reality is often extracted from trajectory data. Okay, so so this procedure mimics the well-known value revision algorithm for dynamic programming, right? And it also can be viewed as the theoretical version or the prototype, the batch version or prototype of more familiar algorithms such as temporal difference or TD. Okay, so if you think about what TD is really doing, when you remove all these complications like target networks, asynchronous update, or and so on and so forth, this is the cleanest version that you get. Okay, So now, if we take this algorithm, but simply change the action selection there from the policy you want to evaluate into a greedy selection, maximize over actions, you recover fitted Q iteration, or FQI, which eventually actually estimates the optimal Q function and thus induces approximately the optimal policy. Okay, and again, like this is like the batch version or prototype of familiar RL training algorithms such as DQN or Q-learning with function approximation. Okay, so for the purpose of the talk, you can think of, we first run FQI, potentially with different neural architectures, different learning rates, and so on. And you get, they approximate Q star. They output some function that approximates Q star. And you greedify that value function, you get a potentially near optimal policy, but some of them may be bad. And you plug them into FQE, which tells you how good each policy is. Right? And then you say, OK, I picked the policy that has the highest evaluation. OK, so what's the problem? So if you think about this problem, actually this paradigm, this pipeline that I'm giving you here is absolutely ridiculous in the following sense, right? So what we have here is, so like we're trying to do something like hold-out validation, right? Where the purpose is often to tune the optimization parameters and neural architectures and so on and so forth for training. But then the validation procedure itself is a complicated algorithm who has nearly identical structure to the training algorithm. So if this procedure tunes all those parameters for training, who tunes this? Right? So this is actually like a big chicken and egg problem that has basically existed forever, and just nobody is talking about it other than me. And but to me, like this is like the real bottleneck to many real-world deployment of offline RL. And in fact, a couple months ago, we had a visitor from Meta who is like working on RL for recommendation systems. They have some like really long-term optimization problem, and he literally asked me, "Is like, I run FQE, but I absolutely don't know whether I should trust it because if I change the neural architecture." They all give like reasonably looking results, but they're just all different. And basically, you have no reasonable way to tell like which one is more correct than others. Okay, so now the question to ask is like, okay, are there alternative methods that can actually help you do validation in a really genuine hyperparameter-free manner? Okay, so it turns out the answer is yes, and you can do this so-called importance sampling method. So recall that we have this problem because the data policy, when you collect data, you choose actions different from those you would like to choose for the candidate policy, right? And that's only natural because when you collect the data, you didn't even know what a good policy is. How can you actually just know like what action to choose? Now, what the importance sampling framework says is that first, it requires that you have randomized your action choice during data collection. And roughly speaking, in a super simplified way, essentially what you do is that you only look at those data points during data collection that randomly just happens to match the target policy you want to evaluate, right? So if you do it properly, you get unbiased estimate, but at a cost of higher variance or viewed it in another perspective, effectively a reduced sample size. Okay, so this works very well in many bandit scenarios, which is essentially one-step RL, and has seen like industry deployment. But it actually has a big problem in multi-stage decision making. That is, first, you will need trajectory data. And second, you need to throw away every single data trajectory whenever there is a single action mismatch in that trajectory. Okay? So as you can imagine, then the remaining samples that are still useful that you can keep around, that size is just like an exponentially small fraction of your overall data set. Now, some of you may know that you can use things like control variance and the doubly robust estimator to reduce the variance of importance sampling estimators. We've tried that, and it helps. But fundamentally, if you have a stochastic environment, the exponential variance just won't go away. Okay. So if you want to evaluate policies in a hyperparameter-free manner, it seems like a dead end, at least for now. But this is not the end of the story, right? So let's take a second look at the training algorithm, right? So we fit a approximate function that approximates Q star, the optimal Q function, which is this guy. and then greedified it into a policy. So instead of like looking policies directly, how about we look at the value functions, right? So the hope is that value functions are objects that have richer information and more structures than the policies. So maybe there's a hope that we can actually compare these for different algorithms in a more effective manner. Okay, so here is the reformulated problem. You run different training algorithms, and you get candidate value functions, F1, F2, F3, and so on and so forth. We have a holdout data set as usual, just the state action reward next state tuples. And the task is that if one of the candidate functions is close to Q star, we would like to find it out, right? And to eliminate degenerate solutions, we're going to require that the holdout sample size to be small in the sense that it should have no exponential dependence on the horizon, or you're just happy with important sampling. Neither should it have explicit dependence on the number of states. Otherwise, you can just take a tabular approach. Okay? Furthermore, don't tell me to use any further function approximation that says, oh, we can solve this problem if here's the object you should approximate, and let's write our neural net to approximate that. No, right? Because then, how do I choose the parameters of that neural net? Right? So no further function approximation. So pretty much F1, F2, and so on. And then the data set, like all the symbols you can use to write down your algorithm is on this slide. You can't use anything else. Okay? So in fact, let me further simplify it. Let's say we have only two functions, F1 and F2. And I tell you, one of them is exactly Q star. And we had no idea how to tell them apart. Okay? So, you may not believe me, but so let me tell you, if you actually think deeper into this problem, what would be the very first idea you would come up with? In fact, someone considered this nearly 30 years ago, Lehman Baird in 1995. He thought about this problem, of course, not through holdout validation because offline RL was not a thing then, but he thought about it through the lens of training. Right? And we'll see like this training perspective will be crucial to the resolution of our problem here. And also connects the problem we're trying to solve to some of the very core algorithmic challenges in modern deep RL. So Baird's question was pretty simple. He asked, I want to do value function estimation from data. Can I formulate it in such a simple way that says I can write down a loss function, loss over different candidate functions, such that value function estimation can be written as the minimization of this loss, and the loss can be estimated from data. Okay, sounds familiar? Well, that's how we do machine learning in most of the case, right? You have a loss, you estimate it from data, and you just optimize it. Now, unfortunately, for most of the algorithms based on, how does this connect to model selection or holdout validation, right? Because if this is true, we can immediately solve holdout validation by just letting the function space to be the set of candidate functions we're selecting from, right? So after all, validation is just like essentially a secondary training process on a different data set with a finite and manageable hypothesis class. Okay, so for some of you, like maybe the reaction was like, wait, the current algorithms are not like that. Well, they're not, right? So for most of the dynamic programming-based algorithms, what you do, as we mentioned before, is to solve a sequence of least square regression problem. So when you solve the least square regression, it's optimization. But at a higher level, it actually has an iterative nature. Right? So you can't write down a single optimization objective and say, this is the thing I am optimizing. So the iterative nature is also at least partially responsible for all kind of various training instabilities that you actually see in deep RL. Okay, so in theory, it can be shown that these iterative algorithms all suffer from serious issues in the sense that there are very simple environments where you can show that these algorithms will diverge even with infinite amount of data, one-dimensional linear function class that perfectly represents the target value function you want to learn. Okay, I don't know like what else like better, what other better properties that you can imagine. Right, so now the thing is that but we still have like tons of RL theory papers, right? So how do we get around of this issue? So in RL theory, the typical thing we do is that we often introduce this so-called Bellman completeness assumption that asserts that the function space we're using not only captures the Q star, the target function we want to use, but also is closed under the Bellman operator. That whenever you take a function in the class, do a Bellman update, it's still within the function class. And of course, it's an assumption because in general, that's not going to be the case. In general, like even if your function space captures the target function, if you look at other arbitrary function, do a Bellman update, generally they will take you out of your function space, right? And some can argue that maybe this assumption is reasonable for, if you use rich neural net and rich continuous hypothesis class, but for holdout validation, where your hypothesis space is just a handful discrete hypotheses, well, this makes absolutely no sense. Okay, so long story short, replacing iterative algorithms with a single optimization is kind of a dream in RL. And if we can do that, we will immediately solve our model selection problem as well. So why is it so hard? Okay, so to understand the difficulty, let's come back and see what Leon Baer did, right? So what his reasoning was the following, which is very natural. We know that Q star satisfies the Bellman equation, right? So how about we just take the difference between the two sides of the equation, okay? So that's and make that a loss, right? Now the difference between equation is still equation. It's the equation. Sorry, it's still a difference between functions is still function. It's still a function of state action pairs. So we take the square of that and take expectation over some distribution over state action pairs that we see in the data. Okay, we have a loss. And in fact, this is what people tell you, like in empirical papers, when people are not careful, is they say, oh, RL is about minimizing Bellman errors, and this is a Bellman error. Well, they're not, right? They're iterative algorithm that you see in the previous slides. Okay, so why don't people do that? Because we can't. Like if you actually write down this loss function, you will see that the tricky part is that you have a conditional expectation which corresponds to the Bellman operator inside the square. And we know that that's the thing you don't like in estimation, right? If you have a conditional expectation inside the square, it means that you can't directly estimate it. If you use the naive estimator, sometimes we call it the one sample estimator, which just ignores the conditional expectation and use the random next state you see in the data, it's known to be a biased estimator. You have an extra variance term over here that varies across different candidate functions. So you just can't, unlike supervised learning where the inherent label noise term is the same for all predictors, even though you know that you have this extra term, you can just ignore it. So here it's not safe to actually ignore this term. Okay, and historically people have been thinking about how to debias this problem. Well, it turns out that either it requires a simulator, that if you can sample two IID next states from the same state, you can easily come up with an unbiased estimator. And this procedure is called double sampling, and which is how this difficulty got its name. It's often referred to as the double sampling issue or double sampling difficulty. Or you need a helper class that you need additional function approximation to approximate the Bellman update of your candidate functions, which is again like introducing chicken and egg in our problem. Okay. So having seen the difficulty of the problem from the lens of training, I'm now going to tell you how we solve the problem, okay? So to remind everyone, the problem I want to solve is that I have two candidate functions, f1 and f2. One of them is q star. I want to find it out, okay? And to understand our solution, we need the old result for training by Jeff Gordon actually around the same time. Recall that all these dynamic programming algorithms in RL generally are unstable. Like they can diverge, they don't have guarantee if you only assume realizability of the eventual function you want to learn. Now, if linear doesn't work, maybe something simpler can work, right? We know like tabular works, but is there somewhere in between tabular and linear? Well, it turns out yes. So if you use piecewise constant function class during training, or like in approximate dynamic programming, you are guaranteed stability and convergence. So what this does essentially is to partition your state space or state action space into different groups, and you're essentially treating all states in that group as equivalently as some kind of mega state, right? And this is like studied in the so-called state abstraction or state aggregation literature. So and here the piecewise constant function class is essentially equivalent, just a different representation of the partition that induces it. So for the rest of the talk, I'm going to refer to these two things like interchangeably. Now, this is for training, but we can also translate this result for our validation. Namely, if someone gives us such a nice function class, or the partition over the state space, which I'm going to call G in the context of validation, then there are millions of ways that I can use it to pick out the right Q function. Like one way among many that I can do is that now I can actually estimate the so-called projected Bellman error. And this can be estimated from data. And it's guaranteed that if this is small, I can pick out the correct Q function. But technically, what kind of conditions we need for this function class? Well, you need three conditions. One is piecewise constant. We just talked about it. Two, realizability, that this function class can express Q star. Okay? And third, it needs to have a small number of partitions, because that governs the statistical complexity of estimating anything involving this class. Okay, so this is the approach we're going to take. And of course, the question is, who gives you this nice magical function class G, right? If I require it as additional input, that's just like yet another chicken and egg. So now we're coming to the very last step of our approach, where I'm going to tell you that we can actually create this magical function class G out of nothing, essentially, with some caveats. Okay? So as a first step, what we need to do is to verify that this magical G always exists for an arbitrary MDP, possibly very, very complex, high-dimensional, and so on. Well, good news is that it always does. And here, because I'm only proving its existence, I'm going to pretend that I know everything about the MDP, and I'm going to give you a constructive proof based on these information I shouldn't have. Right? So how do we do it? Well, it's actually very, very simple. So see, here is the ground truth Q star function of the MDP, right? What I'm going to do is that I first discretize the output value of this Q star, where I pay a small discretization error, which is totally OK. Then what I'm going to do is I'm essentially going to call all the state action pairs sharing the same discretized output value as the same piece. Even if, and I can totally aggregate together regions, here shown in orange, even if they're quote unquote far away from each other in this state action space. And as you can see, this totally works. Here I'm using a 1D visualization, but even if your state action space is super high dimensional complex, this still works, right? It's guaranteed to be piecewise constant, and the construction guarantees that I can approximately represent Q star. And furthermore, how many pieces are there? How many pieces do I get? 1 over epsilon, right? Because epsilon is the discretization error, because 1 over epsilon is essentially the number of possible discretized values that the function can take. And I think people are getting it, but this is often the point of confusion. So I actually created a more extreme example. Let's say I have a function fx. Let's say this is my value function that takes value 1 on all rational numbers and takes value 0 on all irrational numbers. Under my definition of piecewise constant, how many p's do I need to represent this as a piecewise constant function class, a function? 2, right? Because all rational numbers is one piece, all irrational numbers is the other piece. Okay? So it's so we're completely ignoring the topology, the native topology of your state action space. We're building that topology out of the output of this function. Okay? And in fact, this is, roughly speaking, how we're going to construct this magical function class G. But of course, you have the problem here that this construction depends on Q star, which is our ultimate learning goal, and of course, you don't have access to. Okay? But now I claim that we're basically done. Going back to this question, recall that the model selection or Hilda validation problem, we have two candidate functions, f1 and f2. We want to know which one is Q star. We know that if someone gives you this magical G class, this partition, that satisfies those criteria, I can do it. Now I need this G class. How do we do it? Well, you just partition your state action space according to both functions simultaneously. Okay? So it satisfies all the conditions before, and the number of partitions you get, because now you're partitioned over according to two functions, you get 1 over epsilon squared instead of 1 over epsilon. This is not as good as the ideal case, but it's not bad at all, like, given how we had absolutely no idea to solve this problem before. Now, this is for 2 functions. If you naively extend this to multiple functions, things will quickly get very ugly, right? Because then the number of partitions you get is 1 over epsilon to the power of number of candidate functions. You don't want that. So what we do is that you actually do a tournament procedure, that you run this procedure for every pair of functions in your class and do kind of like a minimax. I'm not going into details here, but you can show that you get a sample complexity bound for this procedure with polynomial dependence on horizon, 1 over epsilon, log number of candidates just straight out of like union bounds, and a coverage parameter that is standard in RL guarantees that measures how your data distribution covers the distribution of states induced by different policies. There's some nuances there, and that is a whole topic on its own because this notion of coverage is so central to modern RL theory, especially in offline RL. I have several talks just dedicated to that topic, but that's not the topic today. And furthermore, when you try to implement this algorithm, a concern you might have is that, oh, we're talking about this kind of like weird, potentially super weird partition that will need to partition all all rational numbers as one piece and irrational as the other piece. How can you even possibly analytically represent this partition? Well, the good news is that to actually implement this algorithm, all we need to do is to do that projection step over the data we have, the holdout data set we have. So it turns out that all you need is that you need to look at the data points in the holdout data set, and all you need to tell is like which data points belong to the same group. And that's trivial to check. So therefore, you can very easily implement this algorithm with all closed form expressions. No optimizations, no approximations, nothing. And we actually did it. So this is experiment results for holdout validation in some GIF environments, also some Atari game, like a video game environments with high-dimensional visual inputs. You just implement the algorithm like literally as is, without any heuristics or approximations and so on. And not going into details here, but you get a very promising performance and a good sample efficiency. OK, so that's the main part of the talk. And question?
What happens if you remove the realizability assumption?
So I guess what you mean is that what if Q star is not among the candidates? So the thing is that if you still have it as a, if you still have a good enough approximation, you will still be able to do the analysis, but the approximation error is going to creep into the final bound. And in a way that is worse, right? So if you think about it, this tournament procedure is very similar to things like Schaffer tournament for total TV distance minimization. And as the case for all these like tournament-like algorithms, approximation errors are amplified much more than more standard like ERM settings, where like how much approximation error you have, you just get that directly into the final bound with a multiplicator of like 1. But here, I mean, in RL, it's always the case that whatever approximation error you have is going to be amplified, with like horizon and so on and so forth. But here it's just like even worse than that. So that.
In non-parametric estimation, like a constant factor is like 3 or something.
So yeah, so again, the thing is that in RL, even in standard, well-studied settings with all the good conditions, it's not going to be constant. The amplification factor is often involves like a horizon factor. It's very bad. Like we're not even talking about this, which is an even more difficult problem.
So can you explain intuitively why in your tournament, like let's say if opt is the best possible loss you can get from any function in this family F that you have, the final error would not be a constant times opt and would be worse?
So, OK, so I'm not sure I can explain it very, OK, how to put it. So, OK, so I don't even need to talk about my algorithm. So let's just look at this very simple procedure of let's say someone gives you this magical G and just learn of it. OK, so if this magical G can only represent Q star up to epsilon accuracy, generally if you run your algorithm on top of it, you get something like epsilon over 1 minus gamma. So you already pay a factor of horizon. And this is like the most standard, simplest possible setting of using function approximation in RL. And I don't know how to, so maybe here's a vague intuition is that.
Problem is with
No, it has nothing with tournament. You already have all those applications in every single algorithm you can see in RL.
I think a good way of like seeing this is like you might get like a constant approximation to like the value of like that tournament objective itself, but you need to translate that into a bound on like how good is the actual.
Yeah. So maybe here's another way to think about it. So this function space can represent Q star up to some epsilon, but you're not saying like in supervised learning, what you do is that you use this function space, use the function in the space to directly approximate your target function, like with some noise. But the way you use it in RL is different. You use it in dynamic programming, which is an iterative algorithm. You use it again. So every time you use it, the factor of approximation goes in once. So like a factor of horizon blow up is expected everywhere.
You could have said, how well do you estimate the best F in your class? This is not an RL question.
Right.
But then you're saying you'll just get a constant block then?
when you go to me, if it's not, I want to see your paper.
What do you mean by how well you estimate?
So, I don't know, I'm just going to look at the Q function error. So there's some Q star, it's not in my class.
Right.
I give you F1 through Fk,
Right.
and I say pick the best one up to the closest approximation to Q star in some norm, not related to dynamic programming.
Okay.
Will I get a constant approximation?
No.
No?
Okay. Of course not. I mean, it's the same thing here. I mean, the other thing is that you, like in RL, like there are several things. It's like, for example, when you say I have the function, I have the, this is the conversation I was having before the talk. Let's say, like, how do you even measure the norm between F and any candidate in F and Q star is not even clear. Like, if you, like, the standard thing in the old literature, you use infinite norm, but that's like too stringent because the thing is that people don't know how to deal with distribution shift and all of that. So that is already stringent. You can't really get any infinite norm guarantee. So you need to use some like weighted 2 norm. But the question is like, what kind of distribution you measure your weighted 2 norm on? That's even unclear. So not only you pay factor of horizon, you also need to pay this distribution shift factor, which is like related to the coverage thing. So like, I get the level of distrust, but I promise you that I have taken Learning Theory 101. I have seen how these approximations works. I've worked through like Chauvet tournament. I know how approximation tournament works. I guarantee you that this dynamic programming nature of RL, as you can see, like the core difficulty we're running into here and before is that when you get multi-step decision making, like things like importance sampling get exponential variance. Okay, so something dramatic is happening when you have a non-constant number of decision stages. And if you only see a polynomial blow up, you say, voila, like that's the best thing you can have in the world. Okay, constant, like, sorry, no.
I'm curious about the optimization here. So you're, I'm just worried about the runtime being linear in the number of.
Yes, it is. So you can't use this for training. Yeah, it's only for model selection.
So you can like reduce it to some search problem on the space that you might hope to do in time much smaller than linear in size.
So at least we haven't. Well, I guess one thing you can do is like maybe you can divide concur, like divide into subgroups, run the tournament in there, and so on. But I think that will compromise.
Very little.
Yeah, or I mean, it's actually not even linear. Like it's quadratic.
Yeah, so that will say. Wait, why is it quadratic and not?
Well, I need to do pairwise comparison among all pairs of candidates.
Oh,
Yeah.
I thought you said it's like a tournament. Like,
Yeah, it is.
That's n log n, not all. Wait.
Sorry,
Oh,
what?
you really have to do all pairs, so it's really crazy.
Yeah, you need to do all pairs.
Okay, so you can say that we just n log n, but there's no way to like reduce the search problem.
No, I don't think so. I mean, or like maybe like given how difficult the problem is statistically, like I didn't even worry about computation. Like, if I have if I need to pay 10 times computation to get as you can all realize, like there are all these unusual blow-ups that are super bad if you view it from like standard learning theory perspective. So if there are ways to actually improve the statistical property of this by a tiny bit, I'm willing to suffer like 10 times computation. But we just don't know ways to do that.
What Matt is alluding to is that there are faster versions of the standard Cepheid tournament that do not need quadratic time. They can be done in almost linear time by some tricks. And maybe it would be interesting if you cared to enhance your method to make it faster. But you're saying this is not the goal. The goal is to get something that's...
Yeah, so that's one thing. And I think Cepheid tournament and here, there's still something that is different, right? So in Cepheid tournament, when you're comparing two two candidate distributions that are both far away from the ground truth, what you do is that you still define the subset of your sample space and measuring the empirical frequency of samples in that subset, right? So in some sense, whatever you estimate there is still unbiased, and it just lacks power to distinguish between the two distributions or tell which one is closer. But here, the situation is worse because if you see, we're using this projected Bellman, we're measuring this projected Bellman error. This G come from the construction, which is constructed from the current pair of functions, and this G is only good if it can represent Q star. So when you construct it from a pair of functions that are both far away from Q star, it's like you have a judge that itself is very bad. This quantity itself will lose all kinds of necessary fidelity for it to even make sense. So the situation is even worse than Cepheid. So yeah, so this is actually an old talk. I mean, I'm a little guilty of reusing talk, but I thought I would talk about some newer stuff, but I guess I can only gloss them over. So we have an extension to this policy evaluation recently, and realizing, so basically the whole thing is actually a recipe that says, if you can find a base RL algorithm with the extra kind of stability that usual dynamic programming algorithms don't enjoy, you can basically plug that into our recipe and get a model selection algorithm. And unfortunately, in RL, there are not that many algorithms that satisfy this criteria. But if you focus on policy evaluation tasks, it turns out there is. The only other algorithm we know, which is the algorithm forgotten in the literature called LSTD, and we actually turned that into a new model selection problem where your target is to select for Q pi, not Q star, and actually it also works extremely well empirically. And also here's kind of some discussion, as I said, whenever I talk about this, many people's first reaction is why don't you take a model-based approach? I think when they say that, literally what they had in mind is that they want to build a tabular model based off holdout data and use that model to evaluate your policies. Of course, that's not going to happen. And whenever you build a model, in realistic problems, you need function approximation, you need all these hyperparameters. So it's another chicken and egg problem. That said, model-based approach does have a pretty significant advantage. That is, you can possibly do tuning, do holdout validation, do model selection at the model learning stage. And once you learn the model, you just trust it, right? And why is that? Why is that? Because the model learning step is basically like a supervised learning problem. You're predicting the next state based on current state action pair. So there's a ground truth, which is next state. So you can basically use potentially all kinds of things you like in supervised learning to do model selection. Except that there are all kinds of caveats with that. For example, you can have a model that's making a mean prediction plus some noise, and you'll say, okay, how about we use a loss that is the real next state in the data and minus the model prediction, which is a random state, and say let's take some norm. Well, first of all, the norm is an arbitrary design choice. And second, really if you have a stochastic system, really what you should do is to compare the transition distributions of your model with the transition distribution of data. So a proper loss you should use is something like Wasserstein. And if you use this, you'll suffer all kinds of issues. I don't have time to go into this. And something people do is also, I don't directly learn a raw model that predicts next state from the current state. Instead, I jointly learn a representation that maps the raw observation down to some much more compact, low-dimensional state space, and learn a latent dynamics G over there. Hopefully, that'll ease some of the questions. But then it's actually unclear what's the right loss you should use. Many people would think about use the loss of say, oh, let's just use prediction loss at the latent level, ignoring the stochasticity issue there. But even here, this loss is actually degenerate and problematic because you no longer have a ground truth that is unmanipulable, that cannot be manipulated. Because you're jointly selecting phi and g. Whatever you select for phi, this compression will also change your label phi of s prime at the latent level. As you can imagine, I can select for a phi that throw away all the information in the raw state to give you a very easy prediction task at the latent level. So there are a lot of interesting complications there related to the bisimulation theory for MDPs and stochastic processes, and we have some recent works with Dylan that addresses these questions. And there's a final slide that talks about, well, what if you really have to do model selection over simulators or dynamics models? And my recommendation is actually to reduce it to the value-based case, at least if your goal is policy evaluation, because really, in the value-based case, the concept we focus on is this Bellman error. But it turns out that Bellman error is also secretly a model-based loss. It actually can be written as an IPM between the candidate approximate dynamics and the ground truth dynamics. And what is really nice is that even if you have high-dimensional state space, this IPM actually projected down into a single dimension, a scalar value. And this is the most relevant thing for your ultimate task if your task is, say, policy evaluation, predicting the performance of a policy. OK, so in the interest of time, there are some interesting future directions I'm interested in. I'm happy to talk offline about it. But otherwise, thank you.